Somewhere in a data center right now, an AI model is being trained. Not a small one, not the kind you interact with through a chatbot on your phone. We're talking about a model with 671 billion parameters, a system so large that even describing its scale requires a pause. 671 billion mathematical weights, each one a tiny decision about how the world works, stacked and layered until something resembling thought emerges. Until recently, training something like that would take days, weeks, tens of millions of dollars. But something changed in early 2026, quietly, without a product launch or a keynote moment. And almost nobody outside a small circle of engineers understood what it meant. To understand what changed, you need to go back to something most people never think about. Every AI model is, at its foundation, a collection of numbers. Not metaphorically, literally. Numbers that get multiplied, added, transformed, and compared billions of times per second. The precision of those numbers, how many bits of information it takes to store each one, determines everything. How much memory the model requires, how much power it draws, how fast it runs, how much it costs. For decades, more precision meant better results. 32 bits was the gold standard, then 16, then 8. Each halving felt like a compromise, a sacrifice of accuracy for the sake of speed. And for a long time, that trade-off was real. FP8, 8-bit floating point, became the new frontier. NVIDIA built an entire GPU architecture around it. Cloud providers restructured their data centers for it. Companies made multi-billion-dollar infrastructure bets, assuming FP8 was where the line would hold. And then, quietly, someone decided 8 wasn't small enough. NVIDIA introduced NVFP4, 4 bits, half the size of the previous standard. On paper, that sounds like a regression, like throwing away half your thinking capacity to save on storage. But that's precisely the assumption NVFP4 was built to destroy. On NVIDIA's Blackwell Ultra GPUs, NVFP4 delivers 15 petaflops of dense compute. That number, 15 quadrillion operations per second, is 3 times what FP8 delivers on the exact same hardware. Not a new chip, not a new factory, not another round of capital expenditure. 3 times the output from the same machine. That 671 billion parameter model, DeepSeek R1, one of the most complex AI systems ever built and deployed at scale, was put through a standardized training benchmark. 512 Blackwell Ultra GPUs working in concert. And they completed the benchmark in 64 minutes and 36 seconds. 64 minutes. But here's the part most coverage missed entirely. The story isn't speed. Speed is just the surface. Underneath is something far more structural. Precision is a tax on intelligence. That's the mental model. Every bit you add to a number makes it more accurate and more expensive. More memory, more energy, more time per operation. The assumption, for decades, was that you needed high precision to preserve the integrity of the thinking. That rounding errors at the bottom of the stack would compound upward and eventually corrupt what the model understood about the world. What NVIDIA discovered, through years of what they call extreme co-design, designing hardware, mathematics, and software simultaneously as a single unified system, is that this assumption was only conditionally true. The old 4-bit format used blocks of 32 numbers, sharing a single scaling factor. Coarse, imprecise. The rounding errors did compound. The accuracy did suffer. NVFP4 uses a different encoding. Blocks of just 16 numbers, finer grain. The mathematics inside each block is more carefully structured, allowing the format to represent very small and very large values with significantly less distortion. The result is a format that occupies half the space of its predecessor, but loses almost none of the intelligence. This wasn't an accident. It was designed, deliberately, across every layer simultaneously. And that's where the hidden system starts to appear. NVIDIA designed the format. NVIDIA etched it into silicon. NVIDIA built the libraries that convert models into this format. NVIDIA makes the inference frameworks that run those models. NVIDIA hosts the developer ecosystem where those models are published, downloaded, and deployed. Every single layer of the intelligence supply chain, from the physics of the transistor to the API call your application makes at runtime, passes through NVIDIA's design decisions. This is not coincidence. It is the deliberate product of co-design. The strategy of optimizing hardware, software, and mathematics as one coherent system creates something economists have a precise term for: switching costs. Not because competitors are incompetent, but because leaving requires rebuilding everything at once. Each company adopting NVFP4 is not just optimizing a workflow, they are deepening a structural dependency. And yet, and this is the detail that changes the entire frame, the dependency runs in both directions. Follow the money. When compute gets 3 times more efficient, the cost of running a large AI model collapses. Not immediately. Infrastructure takes years to migrate. The cost per million tokens of AI output, already falling, falls faster. Cloud providers compete on margin, not capability. The commodity layer becomes commoditized. And when that happens, the value doesn't stay at the hardware layer. It migrates. Not to the chip, not even to the model, but to whoever controls the relationship with the end user, the interface, the data, the context, the trust. The efficiency gains don't benefit everyone equally. Companies already inside the ecosystem get the 3x immediately, without new capital expenditure, by changing a configuration flag. Companies outside face a more complex calculus. Migrate and gain the efficiency. Stay independent and pay a structural cost that grows every year as the gap widens. That's not a technical choice. It's a strategic one, and increasingly, it's a geopolitical one. We are in a race, not just between companies, between nations. The United States, China, the European Union, Japan, India, every major economic power has concluded that AI infrastructure is sovereign infrastructure. That compute is the new oil, the new steel, the new electricity grid, and that whoever controls the factories of intelligence controls a critical lever of the 21st century. In that context, a 3x efficiency improvement is not just exciting, it is geopolitical. A country that can run the same AI workloads at 1/3 the energy cost has a structural economic advantage. A company that can train models 3 times faster can iterate 3 times more quickly, can discover capabilities 3 months earlier, can reach commercial deployment a full quarter ahead of a competitor running older formats. And NVIDIA's next platform promises 3.5 and 5 times beyond what exists today. Which means the gap isn't closing, it's accelerating. There are 2 versions of where this ends. In the first version, the efficiency gains concentrate intelligence. One architecture, one company's design philosophy embedded in every layer of the stack. Intelligence optimized for the priorities of whoever holds the deepest lock on the infrastructure. In the second version, something different happens. When compute gets cheap enough, when the intelligence tax falls low enough, a researcher at a university in Lagos can train a model that would have required a supercomputer 5 years ago. A hospital system in a country without major cloud infrastructure can run clinical AI locally on hardware that costs a fraction of what it once did. The line between who builds AI and who only consumes it starts, slowly, to blur. This is the civilizational bet embedded in every efficiency gain. Not that AI will be free, but that the cost of access will fall faster than the cost of everything else. That the arithmetic of intelligence will eventually favor wider participation over narrow concentration. Whether that bet pays off depends on decisions being made right now, in boardrooms, in legislatures, in technical standards committees that most people have never heard of. And in the quiet choices of engineers deciding, format by format, what the infrastructure of intelligence is built to optimize for. The technology is not neutral. It never was. In 5 years, this format is already yesterday's conversation. The next platform is standard. Inference is cheap. Training costs have dropped by an order of magnitude for most model sizes. The question has shifted from can we build this to should we, and who decides. In 10 years, the layer that matters is no longer compute. It's alignment, governance, and application. Which countries built their own stacks? Which remained structurally dependent? The workforce has been restructured in ways the people most affected were least prepared for. In 20 years, the 4-bit number feels the way the printing press feels now. Not a technology, a turning point. A moment when the cost of accessing a certain kind of intelligence fell below the threshold of scarcity. And what humanity chose to do with that access, whether it concentrated power or distributed it, was decided in this decade, in these years, in choices that are happening right now. A 4-bit number. That's where this story started. A small, elegant, deeply engineered compression of mathematical precision. A format that fits in less space, runs on less power, moves through silicon in half the time of its predecessor. But look at what it carries. Inside that tiny format is a theory of how intelligence should flow through civilization, a bet on who deserves access to cognition, a structural wager on whether the systems shaping the next century will be owned by a few or available to many. The engineers who built this were solving a technical problem. They solved it elegantly. But the larger question, the one the number only touches, is still open. When intelligence becomes infrastructure, the way roads became infrastructure, the way electricity became infrastructure, the way clean water became infrastructure, who decides what it's for? That question doesn't have a technical answer. It has a human one. And we are the generation that has to give it.